Okay, hello Ochem. So today I'm going to attempt to explain Enol and Enolate with you in about 15 to 20 minutes. Okay. Okay, so what is a nucleophile and an electrophile? That is my first question for you. So if you remember, you can recall that a nucleophile is the agent that's going to attack the electrophile, and the electrophile is the agent that's being attacked. Okay, so we have always learned that ketones or aldehyde are usually the electrophile because they get attacked by another nucleophile at the carbonyl carbon, and that nucleophile is added to our ketone or aldehyde like this. So throughout chapter 19 and 20, we look at ketones like an electrophile, an agent that's kind of passive and attacked by people. But when we get to the realm of chapter 21, we see that we can somehow activate our ketone to become a nucleophilic version of itself. So a stronger, more potent version that could actually go and attack people. Okay, and since it goes and attack people, you have to activate it. So how do we activate it? We have two ways to turn it into a nucleophile or a ketone that has this alpha carbon ready to attack people. Okay, so there are two conditions to turn a ketone into a nucleophile. The first one being the acidic condition. Let me erase this real quick. Acidic condition tells you that in the first step, you have your carbonyl oxygen protonated. Also, this is called tautomerization. So it comes from the keto to the enol form. Usually happen in your body system too. So you have this being your product of the first reaction, and then you can just have a molecule of water to go in here and eliminate this H. H goes back here, this goes up here. So you end up with this guy. Okay, and you call this guy an enol. You call it an enol because it has an alcohol in there. Okay, and this double bond right here functions like a nucleophilic part of your enol. So if you are presented an electrophile like a halogen, let's say Br2, this double bond will come in here and attack this Br, and this Br comes back here just like normal mechanism. And that is when we have this. And remember to add in one plus charge right here, being the carbocation intermediate. And then one of the resonance structure for that is when you shove this lone pair down here to form a double bond O, OH right here, so that you have shifted your plus charge from the C up to the O, right? So just like that, and then you abduct that H right here by another molecule of water, and then you have your alpha brominated ketone. Okay, so that means you just added, just a fancy way of saying you just added a bromine to the alpha position of your ketone. Okay, so that was the acidic condition. How about the basic condition? In the basic condition, we have a pretty straightforward method. So still start with your good old ketone. Now we have to choose an appropriate base. What do I mean by appropriate? We want to use a base that cannot act like a nucleophile. Because if it acts like a nucleophile, it will go on and attack this carbonyl carbon, and this goes up, and it will undergo addition reaction to the ketone, which you don't want in this case, okay? So, you obviously want to choose an appropriate base. The most often seen one is LDA in our chapter, or nitrogen with two isopropyl groups bearing a negative charge and a lithium ion just balancing it out like a spectator ion. We can also see NaH, bulky bases like DBN, DBU, and NaOT-butyl. All that bulky stuff that cannot or is too bulky to be added to the carbonyl carbon. So what does that base do? It will eliminate or pull out this H from the alpha carbon. Remember, we call this alpha carbon because it's right next to the carbonyl carbon, okay? So if it pulls down this H, then this goes back here and this goes up here, forming this not carbocation, this intermediate that looks like this. Where am I? Oh. Yep, just like this. Or we can also write it as this. It's one of the resonance structure of our product, so we form this. And this, ladies and gentlemen, is going to be your enolate. Actually, both of these are fully functional enolates, but this form is often seen being used in mechanism of this chapter, okay? So this lone pair right here on the alpha carbon is fully functional and ready to come and attack other people. Just like that. And then you have yourself a halogenated ketone. Alpha, I should say, because you are adding that X to the alpha position. So how versatile this reaction could be. You could see first halogens being added. So if you go LDA and then halogen, you get halogen added to the alpha like I just presented. You can also see a chain, an R group being added to the alpha carbon. So whatever the R is will be added right here. And the mechanism is just normal, just like what you've seen. You have after LDA, step 1, you have this enolate, and this enolate will attack the R group just like in SN2, if you recall what that looks like. 2 arrows mechanism that will give you the R in the end. We can also do an aldol reaction in which a ketone or an aldehyde attack itself, okay? So say if you got this good looking ketone and you activate it by firstly putting in LDA, then your ketone will be like this, right? And in this case, if you don't add anything, you will have the ketone just reacting to itself. So what does it look like when you react the ketone to itself? So this ketone is playing electrophile. And this ketone now have become an enolate and playing a nucleophile. So when you have that, you know that when presented with a nucleophile, a ketone will always be attacked at the carbonyl carbons or the carbon connecting to the O with the double bond. So you go there, there. Okay, and then you have the two ketones of the same thing tethered together, and be careful how you draw it too. Should look like this. Okay, and then in the end you can just, oh, what is that? In the end, you can just throw in a molecule of water to neutralize the guy so that he's happy and neutral. Okay. And this product is called an aldol. And how an aldol reaction works, we can go in more details in my next videos or in my next lecture, but you know that it could happen. Okay, or ketone just reacting to the same thing of itself. Okay, back to the case of halogenation though, we have something special that I want to bring your attention to. So you see, if you only want one halogen being added to the alpha, let's make this a pH. So we are stripping off the alpha hydrogen on just one side. So if you want just a mono halogenated product or just one Br group added, you have to use the acidic condition. And the reasons why I can explain to you right now. Okay, but if you want a poly halogenated product, you do the basic condition, or you just throw a base like LDA in the first step and then introduce halogen there. Okay, why is it this case? Why is it this case? You will see that you have 3 Br being added to that alpha carbon instead of just 1. And there's hardly any way to stop the basic conditions reaction midway so that you only end up with 1 halogen being added. Why is it this case? So you see in your acidic condition reaction, when you end up with an enol like this, after reacting it with acid in the first step, you will have this after the step 1 of introducing acid, right? When this double bond go in here and attack the Br2, there is a presence of a carbocation intermediate. Ooh, I missed 1 carbon. Intermediate. Okay, this carbocation intermediate makes the reactions go slow and want to stop in acidic condition. Okay, so when you shove this pair down and make this thing into this, and then you have another molecule of water just going in and take this H away. Ooh, take this H away. You get this. Happy. There's no further reaction happening because of that very carbocation that you have right there. It just hinders further reaction. That's for the case of acidic though. For the case of basic, everything is different, a little bit different, you know. So for the case of basic condition, you don't see that carbocation intermediate. You see that carbocation, it gets destabilized by this Br because plus charge wants electron to donate towards them, but electrons are being pulled away by induction towards the Br because the Br is very electronegative. So it's the Br in this case is destabilizing the carbocation intermediate, making the reaction go slow. But there's no carbocation in acidic, in basic condition. You will see that when you get this and you go in and attack this Br, nucleophile, okay, you end up with this, right? Okay, so here, these H's are so much more acidic than these H's in the beginning, because these H's now, the electrons around them are being pulled over to the Br, making them more de-shielded, making them more unprotected, and want to be stripped off further. So it drives the next reaction of the LDA to happen more, profusely. So right here, you have another H being stripped off, and then another enolate forming, and the attack happens one more time. Nothing has changed. Yep, just like that. Now you have a di brominated, and one more time of LDA, and Br2 will give you this, which is, I should write more neatly. I know you want to observe too, and I'm a very neat writer, but when I'm talking and writing at the same time, I can't manage to write neatly. So this is a trihalogenated product, okay? So you see right here, we have a group called CBr3, which is a very good leaving group, so it can leave, okay? That implies that if you introduce OH minus at the very last step as a nucleophile, you will have this very interesting looking reaction where your OH minus will add right here, just like last time at the carbonyl carbon, and then this goes up. Okay, nucleophilic addition, chapter 20. Okay, you will observe that you have, where am I? Oh, okay, OH here, and Br3 being right here. And if you go to Dr. Enol's class, he always use this term, boom, boom, arrows. It's boom, boom because it happens twice. You have two arrows, and it's just, it makes a little funny sound. Everyone likes it. Yeah, so that CBr3 will leave as a good leaving group, and this O will regain its double bond right there to the carbonyl carbon, and you will end up with this, which is benzoic acid, special kind of carboxylic acid. And then this CBr3 minus group, okay? And CBr3, being a very strong base, will pull off this acidic hydrogen right here from the benzoic acid, making this enolate, not enolate, alkoxide in the end. Okay, and then this is formed, which is called a haloform. Or in this case, the halo being the Br, it's called a bromoform. Yep. So if you want to regain neutrality to this alkoxide, you can just follow up with a molecule of water. This takes the H from here, goes back. So then you end up with benzoic acid again and a haloform. So this reaction is called the haloform reaction because obviously it forms a haloform. So the lesson you got from this is that under the basic condition of an enolate reaction, you can't stop at midway. You will go all the way to the trihalogenated products, and then if you introduce a nucleophile there, like an OH, you will have this CBr3 leave and form a haloform. Okay, I think that's enough for today. We've gone through everything that I consider basic about enol and enolate. Let me know if you have any questions. Bye-bye.